Okay, so we'll start. I hope people will come in and join in a short while. Uh, so we had discussed the DNS part yesterday, the theoretical part yesterday. Today I'll be describing or showing you how to, get these open source codes in Compact 3D and use them. So I'll, so they have, you have to go to this website called in Compact 3D. Wait, my screen is not visible, right? Shit,
Yeah, it's not visible.
sorry. Is it visible now?
Now it's visible.
Yeah. Okay. So you go to this website in Compact 3D. Okay, you'll get some details about the code here. Okay, so if you go to the About section, you'll get a brief description of what the code is, how the code functions. Okay. If you go to the Impact section, you'll see all the recent publications that have come through by using this code. Okay, but you can get the code itself from the GitHub repository. So you can go to the GitHub repository and this one. So these are the repositories here. So you have in Compact 3D, Pi4 in Compact, Quasi in Compact, old ones, and there is this WINC 3D. So we are going to use this one, the in Compact 3D repository. Okay, so there are several folders here and several files here. I'll get to these one by one. First, I'll tell you how to get this code on your system. So if you're using Linux, all you have to do, and that is if you're using Linux and you have set your Git repositories in your system, you have to copy this code, copy and run this code. Okay. So, but in case if you do not have this Git repository or if you're not using Linux, you can download it as a zip format. So if you download it in a zip format, you'll get this zip folder. You extract it and you'll have these files here. Okay, so if you compare it with the folders that you have here, you have decomp to the docs, examples, post, VTK, script, and SRC. So you'll get these folders here. So the extra folders that you're seeing here are the cases that I'm going to run. And I'll show you these. Okay. So once you get this code, you have to, compile the code. So there are several modules in this code. If you go to this SRC file, so these are the source codes. So there are several Fortran, so the code is in Fortran and there are several F90 files. Okay. Let me open these in proper editor. Okay, so see, these are the folders there, decomp 2D, docs, examples, post VTK, scripts, SRC. So if you go to SRC, the main program file is this one, the XCompact 3D F90. And this is where all the modules are, you know, linked to. So we'll come to this again, but first I'll show you how to. I mean, if you're using Linux, you'll have to use Linux in the end. So I'll show you how to get Linux. And once you have these files, you can compile the program using make command, and then you can use this code, use this command to run the program. Okay, and now if you have Linux, then it's okay. And just in case if you do not have it, I mean, and if you're using Windows, you can get the Windows subsystem for Linux. So yeah, all you have to go do is go to the App Store. Search for Ubuntu, and you'll get these distributions. All these distributions are available for installations. So you can choose one of them and install. So for example, I have this distribution 22.04. So you can get it from here. Okay, I'll show you a video of this thing. So once you have this distribution, you'll have to set it up. I think it's this one. This one. Okay, this is another way you can get you can get the Linux distribution is you go to the Windows terminal, run it as an administrator, and you type in WSL -- install, and it will get you the Linux distribution. Okay. Once you get that, you'll have to restart your system. Uh, So before you come to this, you'll have to set up a username and password for your Linux distribution. So if you install it through the App Store, you'll get a graphic interface which will ask you for that thing. And if you install it using the terminal, after restarting your system, you'll have when you run this Ubuntu distribution, it will prompt you to enter this username and password. So once you have set up your username and password, you have to run these codes. Sudo apt get update, then it will ask you for a password. So this will update the system, and then you have to run this apt get upgrade. Okay. So it's just yours, right? Okay. So once we get the Linux distribution, you can you can go to the installation folder. So in my case, it was in. So I'm navigating to that folder now. Okay. So okay, so I'm in my folder here now. So you can see these. So this is the address of that folder, and these are the files inside this thing. So we had decomp2d, docs, post-vtk scripts, and all these folders. And there is this make file. So if you run the command make, it should compile this program and give you an executable. Okay. So the first time I ran it, it failed because I did not had these compilers. So you can get all those compilers by using sudo apt build essentials, install and build essentials. So that will install all the compilers that you want. And with this, you'll also have to install the mpich libraries. Okay. So if you try to compile it without the mpich libraries, it will give you this error. So it uses MPI F90, which it won't found and give you that error. So you'll have to install MPICH as well. Okay, then when you have all these Fortran and GCC libraries and the MPI libraries, you can just run the command make and it will compile your programs. Okay, so the compilation takes some time, but after the compilation is done, you'll have several more files now. So these are files generated while compilation, and you'll have this executable xcompact3d here. So when you are running the program, you have to run this xcompact3d with an input file which will specify which case you want to run. Okay. So Harsh, is this clear? I mean, if you have to install these things on your Windows system, would you be able to do it?
Yeah, I can do it. I just need to go through Google some things and it will possible. I want to ask one thing.
Yeah.
Is this everything like Linux and all these things are installed in the PCs used in ISC in labs?
No, I mean, we have a choice whether we want to use Windows or Linux. But let's say if you want to run this code on a supercomputer, then yeah, those are accessed through a Linux interface.
Oh,
So having some familiarity with Linux is, I mean, required. And it
okay.
is not that difficult either. I mean, once you get
Yeah,
comfortable
it's
with it,
fairly easy.
yeah,
Yeah, it's clear.
absolutely. Okay, okay. So now that we have compiled the code, we can run it. So before we run it, I'll show you. I'll share. I'll talk about how the code is structured briefly. Okay, so this thing goes away. So you have to go to. Yeah, in Compact 3D comes with a user guide, but this is for the older version of Incompact 3D. But still, if you go through it, I mean, it will help you a lot with the newer version as well. So there are a lot of things that have stayed the same. Okay, so uh, I mean, in the last class we had talked about how a differential equation is solved using finite difference schemes. So you approximate your differential equation as difference equations. You initialize the solution. That is, you have an initial condition from which you approximate the right hand side function values. So I mean, okay, let me open this one as well. Okay, so you have an initial condition. With that initial condition, you can evaluate the expression on the right and then integrate in time. Correct. So the integration in time is done using these three steps called the fractional step method. Okay, and when you have the u at another time, you can run it iteratively to get the u velocities at the time that you want. So you initialize the solution, solve the equations, get the convection and diffusion terms. You advance your solution in time. I mean, you integrate it in time. You check whether the velocity that you've got after integrating after the first step, this one, after these steps, whether the velocity field is divergence free or not. Okay, if it is not divergence free, you keep on correcting. So this correction step is applied again and again. Okay, so we check the velocity divergence by solving the pressure Poisson equation. And if it does not satisfies continuity, you correct these things. After correction, you move on to the next time step and run this iteratively till you get to the time values that you want to be at, and then you finalize these simulations by saving these files in your oh, in your binary files, in your output files. Okay. Okay. So the boundary conditions in the code, the boundary conditions that the code uses are for periodic boundaries, it uses 0. So this is, a flag it uses for these boundary conditions. For free slip, it uses 1, and for no slip and inflow or outflow conditions, it uses 2. So for the cases that we'll see, it uses either 0 or 2. Okay. And these are several combination of the boundary conditions you can get. But these are about the numerical schemes. Okay, now let's look at the code. Okay, so the first step is to initialize. Okay, so this is the main code. Screen is still visible, right? If
Yes, it is
anything
visible.
happens, you tell me.
Yeah, yeah, it's visible.
Okay, so this is the main program, and these are, these modules. So it commands it to use these modules, which has several functions defined in it, which the program will call whenever necessary. So the first step was you initiate the solution. Okay, so this is the first command, init x compact 3d. Now, init x compact 3d is a function here itself in this program itself. So this is the subroutine. Now, if you look at the subroutine, it also uses several modules so that are again in the subfolder itself, in src folder itself. And what this subroutine does is it initializes the MPI, the message passing interface, which is needed for your parallel computations, and it reads the input file that you give. So if there is no input file, it has a default input file which it reads. So if you do not specify any input file in your when you run this program, it will run with the default input i3d. But let's say if you define an input file, if you give it an input file, it will read the name of that input file. So this code here, this part of this code here, it reads the input file name. Okay, and thereafter this input file, it's the variables in that input file is read. I think it gets the parameters from the input file from this subroutine. Okay, and if you want to look at what the input file looks like, it's here. Let's go to TBL. Okay. So this is an input file. So it defines the flow type that you're trying to solve. So since this is in the TBL folder, this input file is for a turbulent boundary layer. So the 9 flag is for TBL. You can specify the domain decomposition. So when you're using parallel computations, you actually decompose your domain into, subparts. So the big computation is distributed over distributed over several CPUs. Okay, so you define how many rows and columns you want to divide your domain into. Okay, if you want to picture this, there is another paper I'll show you. This one. It's not this one. Okay. Just turn it. Sorry, someone was at the door, so I had to check that. Okay, so the domain decomposition. Okay, I think I opened this paper itself. So, you have your domain. So this is 1D decomposition. We are using 2D decomposition, 2D, which is called pencil decompositions. So, I mean, if you want to divide your domain into subparts, you divide it like this. And each subpart is given to a processor to get your derivatives and for the convective and diffusive term on the right hand side. So the pencil decomposition looks like this. So how many rows and columns you want to divide your domain into? Okay. So you define that here. Okay, for your TBL simulations, you define your or for any other simulations, all the input files are have similar structures, except it depends on what your domain is like. So you can your domain would change, your number of grid points would change, your Reynolds number would change. So here you're defining the mesh and the domain. Um, you're defining your Reynolds number here, your time stepping parameters. So what time steps you want to use, your first iteration value and the last iteration value. Okay, sometimes so what would happen is that you'll start with an initial condition, you'll run for some number of iterations, but your solution will not converge. So you'll have to start your simulation again, but you do not want to start it from the first iteration itself. Okay, so you want to start from the last one. So in that case, the first one would become 50,000 and the last would be, you know, some the number you get after the additional number of iterations. And with this, you'll also have to, change one thing here. So since you're continuing your simulation, you'll have to change this flag from 0 to 1. Okay, so it will actually read an input file. So this input file would be the last output from the first simulation. So you have your time stepping parameters here. If you want to use any modeling, so if I alias mod, if this flag is 0, it will perform DNS, and if it is 1, it will perform alias. If there are any scalars, you can specify them here. And if you want to use immersed boundary method, this flag has to be 1. Here they're specifying the boundary and initial conditions. So this is the initial condition. For TBL, they start with an initial velocity profile, and if there is any, I mean, noise in the flow, flow with comes with some turbulence. These are the boundary conditions. So like I said, 0 is for homogeneous conditions. You can see it's NCL, Z1 and Zn. So the boundary conditions are homogeneous in Z for a TBL, while in X and Y, they are not homogeneous. You can specify flags for calculating spatial derivatives for time scheme. This dissipation control is it's used when because you're using finite difference schemes. Those numerical schemes had high dissipation at higher wave numbers. So it was not able to resolve those wave numbers. So it uses this in these inputs for that, and also I think for alias simulations. Here you can specify your input and output parameters, as in what is the frequency that you want to write the backup files, what is the frequency with which you want to save the files for visualization. So all these inputs you can specify here. Yeah, so okay, so we'll go back to XCompact now. So all these parameters are read through this parameter file. Okay, then it initiates the decomposition. And it starts once the parameters are read. It actually decomposes the domain, assigns the variables to respective processors. Uh, all those things happen here. So the solution is initialized in this subroutine. So once the solution is initialized, we go to our first time step. Okay. So the first time step here. Okay. So okay, some of these bits of codes are, I think they are specific to some applications. So I've been using the older stable version. So I mean, the code that I'm showing that's on the screen right now is the most recent one. But I've been using the stable version, and I think some of these bits were not there. So uh, this part is not there. But yeah, once you have initialized your solution, you can advance your solution in time. You set the fluid properties, boundary conditions, and then you calculate the right hand side, the trans-ic RHS. You calculate the right hand side, um, then you integrate in time, and these velocities are then corrected. Then the divergence is checked, and if the divergence condition is not satisfied, it solves the Poisson equation and the velocity is corrected again. Once the divergence constraint is satisfied, and whether it is satisfied or not, it is checked here in test flow module. Once it is satisfied, you save these files, and the file saving is done in this part called post processing. Okay, so this is one time step. You repeat this thing again and again, and once the solution is over, you finalize the XCompact 3D. So that's what it does majorly. If you want to get into details, you can explore all these sub modules, as in how these modules are reading and writing, which you would need to do it eventually, because that's the point of this open source codes. It offers you flexibility to uh, get what you want. Okay, so for example, if you want to see how a parameter file reads the input here, so you get to the module which has this parameter subroutine. Okay, I think it's in variables. Well, probably not, but you get the idea. So that's what the major structure of this code is. I've shown you how to compile the code. Uh, okay. Okay, so you have the code, you can compile the code. I'll show you briefly how to run the code. Also, now what it says here, by default, you will be building the latest unstable version of Incompact. By unstable, it means that they keep adding modules or changing the programs in the files. However, once you've downloaded those the in compact 3D codes, I mean your downloaded files won't change unless you have synced your repository with this one. So that's why they suggest you to you know use the stable version, the most recent stable version, which is 3.0, so that you can get using Git checkout version 3.0. And this you won't be able to do unless you set your Git repositories in your Linux distribution. But I mean, it is not that you do not actually need to do that. Yeah, there are several functions which are not available in this stable version. For example, uh, I think you cannot put probes in your flow in the stable version here. Okay. Okay. So is this clear so far? I mean, I've not gone into depths at all. So I just want you to realize what the structure of this code is and how to find. So if you get stuck somewhere, how to find where the problem is coming from. You know,
Yeah,
if
no,
you're in,
generally it's clear.
yeah, I mean, if it is not reading your input file, it is somewhere in the initialization routine.
Hmm.
If you get your errors like your velocities are diverging, well, if your velocities are diverging, your grids are not fine enough. But if you get your point error somewhere else, or let's say if you want to add some subroutine, so where to add that subroutine, which functions to call. So you can find all of these here. Okay, so these are the program files. It uses these decomp 2D libraries. Okay, so these are the libraries it uses to decompose the domain for MPI processes. So you do not change anything here. So these libraries are used as is. So if you go to examples, um, they have several examples here. So this is the atmospheric boundary layer example. You have the input files for that. So for channel flow, they have an example for channel flow, for a cylinder flow. Uh, this is not an example. I think it's some schemes. There is lock exchange flow mixing layer. Sandbox is again something else. You can simulate your Taylor Green vortices. You have TBL. There is an example for wind turbine as well. You can, I mean, I have not explored these. You can explore these yourself if you want. So I'll be demonstrating you three examples from here. One is channel flow, your cylinder flow, and TBL. So your channel flow. So the simplest domain and boundary condition you can have is a cubical domain with with the homogeneous boundary conditions in all three directions. Now the channel flow is inhomogeneous in only one direction. Your turbulent boundary layer is inhomogeneous in two directions. Okay, so and your cylinder flow has actually a cylinder in between a duct. So the geometry is even more complicated there. I don't think yeah, even that is inhomogeneous in two directions. So also there is a difference in the output files generated by the newer and the older version. So let me show you that. If you go to okay, so the output generated by the newer version are stored like this. So this is pp-006.bin. These are pressure files, and these are binary files. So the extension .bin is here. Okay, however, in the older version, the .bin extension was not there. I mean, if you okay, let me finish this thought. Okay, so you have all these binary files. Show you this one, small one. So you have these binary files uh, for pressure, velocities, vorticities. Uh, so again, so the code for cylinder actually saves the vorticity files as well. However, if you look at the TBL data, the TBL one does not save these vorticity files. People, okay. Okay, so yeah, hello Venkana. Can you hear me, Venkana? Yeah, so the TVL simulations, they do not save these vorticity files. And so you can also control what variables to save in. Okay, okay. So the older version did not save vorticity files. So you can also, control what variables to save. You can save your velocity gradients as well if you do not want to calculate it separately. Okay, so and it also saves something called snapshot001.html files. Okay, so these are these files you can read in ParaView for your graphic visualizations. Now, how to, so once you have this data, you have to process them. You can use MATLAB for that. You can also use, ParaView for that. Well, besides visualization, unless it is some sort of isosurface that I have to visualize, I prefer MATLAB for this. So, I'll show you some MATLAB codes to actually read these data. Hello, Venkana.
Yes, sir.
Yeah, so can you hear me now?
Yes, sir. Yes, sir. I
Yeah.
can hear it, sir.
So I think you missed about uh, 47 minutes, but these lectures are being recorded, so I think you can go back to those. And if I mean, if you feel like you have to stop and ask something, you feel free to ask. Okay.
Okay, sir.
Okay. So yeah, I was about to show you how to read these files in MATLAB. Okay. So let's go to. Oh, I haven't shown you the old ones, old data points. So okay, so these are the old data files. They were stored like this, and these do not have that XTMF files which you can use to visualize these in ParaView and visualize for. So that is one good thing about the newer version. Uh, so these are the restart files that I told you about. So if you want, let's say if I want to continue my simulations. So far I have simulations till P266. If I want to continue it further, I'll use this restart file as my initial flow, and then I continue the simulations. For that, I have to again, change that I restart flag from 0 to 1 in this input file. Where did it go? Change this from 0 to 1. Okay, so also these restart files are quite large in size. However, in the newer version, uh, okay, I'll open another folder. So in the newer version, you see these restart files are just 1 KB. So these are not saving the actual data, but these are saving where to get the data from. So they did. I mean the in the older version, the restart files, they're saving the entire flow field, all the variables. That's why they are so large. However, if you look at these, so let's open them in. If you look at these files, these just tell you, I time. So which time stamp to look for. And then I think the incompact code can go and look for those data points and read these variables from there. Okay, so this is one good thing about the newer version. Anyways, we'll move on to how to read this, read uh, the, read the what the data files. Okay, so I have these data files here, and so as I told you, these are binary files. So you have to, so to open those files, you have to create, a file ID and read those files using fread. Okay, so if I move to this one, so how do I have to create a file ID. So UX open. This this comment RB tells it says that I have to read these files, and B is for binary. So big endian. So okay, so it generates a file ID, which is an integer number, and then you can use this to read that file. If read file ID is in basically this. So the second parameter tells you how many data points to read. So I've told you to read all the files. But of course, the data is saved in double precision, so I'll specify this as well. So once you do this, you'll get your UX values. But you see, it's just a column vector. So all the files are, all the numbers are stored in one column. However, the velocities that I have here are for a channel flow, and they are on a three-dimensional domain. So I have to reshape my UX file in accordance with that domain that I have. So for RE600, I had a domain of 257 by 256. So now I have these velocity fields. Okay. So this is the X code. This is all the X, Y, and Z points in my channel flow domain. So let's say if I want to plot my velocities at a um, particular streamwise and spanwise location with as a function of Y. So I'll plot these velocities as at 128, all the Y locations, and 128. Okay, so this is the velocity at that specific location in space. Okay, now since my flow is, it's homogeneous in X and Z direction. If I average it in X and Z, I'll get a spatial average of the velocities. So that spatial average will give me a mean velocity at that point for all Y locations. So this is what I discussed yesterday, if you remember, about spatial averaging. You remember, Harsh?
Yeah, little bit.
What this is doing is basically I'm averaging in X. I'm averaging it in X because my channel flow simulations are homogeneous in X, and my channel flow simulations are also fully developed. So the average statistics I do not expect to change with X. So that is why to get the mean velocities I'm averaging in X, and the same argument holds for Z as well. So I'm averaging it along the first index and then along this third index. So the first one is averaging in X and then Z. And these averages I have stored in U. So if you look here, U is basically, for each wall location I've got for 257 Y points, I've got, uh, one mean velocity. So if I plot this now, you get a smoother curve, right? So all the fluctuations have been averaged out. Okay. So you can use this to read the new files as well. So the new files just have that extension dot binary. That's all. So you can go to C downloads. Let's go to TBL data. Okay, so I have quite a few points here. So let's clear all of them. You will generate a new file ID with ux dash 266 dot, or let's say a good round figure number 250 dot bin. My file ID. Now I'll read this. Okay, I've got my ux as well. So what are my I have to reshape that velocity now. So again, I've got one column vector here. So I have to reshape it to get the velocity at all those grid points. So I go to, for that I need to know what the grid resolution was. So I go to this input file. Okay, so I have 129 in X, 129 in Y, and 32 in Z. So what I do is reshape 29, 129, and 32. Okay, so I've got the velocity. Now, so the turbulent bound homogeneous only in Z direction. So I can average it only along the third coordinate. Okay, so let's do that. So if you see this, this gives me a, uh, velocity profiles at each X and Y location for the turbulent boundary layer. Let's plot it at the last station of this domain. So at the last X point of this domain. Okay, so plot the velocities last X. Sorry, 129. Uh, are you guys familiar with MATLAB commands codes? Are these codes confusing?
No, no, I'm familiar.
You've used this, right?
Yeah.
Okay. Okay, so this is, this is the mean velocity, what the mean velocity looks like at this point. We haven't averaged for a large number of, uh, so we have only used 32 locations to average, so that's why there are still some fluctuations left. Okay, but you see that general shape of that velocity profile curve, right?
Yes.
Okay, so I've shown you how to read these velocities in your MATLAB. Okay, and once you have these velocity data files with you, you can always generate the geometry in the MATLAB itself. So if I go to that folder again. Okay, so if you look at here, so here I have defined the number of grid points, the domain size, dx and dy I can calculate here itself. If you remember, I had told you yesterday that NCompact uses a uniform coordinate to solve your equations, but for boundary flow simulations, we need finer resolution near the wall. Okay, so what NCompact does is it solves the equations in that uniform coordinate, and it gives you the corresponding y values in the real coordinate. So it gives you the actual y values that would be there. So you can import that y value here. So it's okay, let me show it here itself. So it gives you this yp.dat file for the wall locations. So you can read that for uh, your y values. Uh, you can define your x and z values because the grid is uniform there. And again, all these input parameters that we had seen in the input height 3D files. Okay, then thereafter you can read your velocities. So I have, using these as building blocks, I have made this program to read all these u, v, and w velocities in one file. And I use this to get my u, v, w velocities. And then once I have my geometry, that is x, y, z, and u, v, w, I can calculate all sorts of things. So I can calculate the velocity gradients, I can calculate vorticities, I can calculate shear stress, shear strain, um, you know, turbulence, Reynolds shear stresses, production in the turbulent flow, dissipation, all those quantities I can calculate. Okay, so you have the necessary ingredients now. Okay. Uh, okay, so I'll, what I'll show you now how to use these things in ParaView. So the older ones, in the older version, you do not get those XTMF files that I had shown you earlier. Um, so these XDMF files are not there in the older one. So this is the older version. So what we did for this one is we had a code to read these velocity files and save those data in a format which ParaView can read. Okay, think yeah. So you can save it either as .vtk files. So ParaView can read VTK files. There is also .nc file which ParaView can read. So there are .nc files as well. So I had used this .nc to read these in ParaView, and then you can do all sorts of visualizations there in ParaView. But we'll use the newer version output for this thing. So these are the newer version files. Okay, so before now let me just show you. So you open ParaView. Okay, you go to that folder. So you see we are in the cylinder data folder here. So it can read these XDMF files. You see all these 10 XDMF files are stored here in a common uh, file header. So you can just select these and press OK. It will read all those 10 files. You select the XDMF reader for this. Okay, so it will reflect here in this pipeline browser, and these are the variables it is going to read. If you do not want any some variable to be read, like let's say pressure, you do not want to read pressure, you can remove pressure. Okay, and that takes the grid values as well. Once you you know set these parameters, you can click apply, and it will reflect here. So this box that you see is your computational domain for that cylinder. Okay, so now you visualize these variables. So let's say if you want to visualize the u velocity, you have to go here. So it's so this section that shows solid color, you select the variable that you want to plot. So let's say x velocities. And how do you want to plot these? So I'd like to see surface plots for this. So it will plot a surface plot for this thing along with the color bar. Okay. So the circular thing is a cylinder here. The velocities are, so this light blue shade is the zero velocity. Okay. Now in this snapshot, if you remember, there were 10 files. So this is, if you look at here, the top section, it says time zero. So it's the first file. So this figure corresponds to the first file that was read. Okay, so there are 10 such files. The index starts from 0, it will go to 9. So you can look at all these one by one using these play and forward and backward buttons. So if you go to next frame, you'll see the next frame here. Okay, you can keep going till next. So it will you see the flow developing here, or you can just play it once and it will play like a movie. Okay, so these are the velocity x velocities. You can also look for y velocities. Okay, so the y velocities are positive here and negative here. You can look for z. Of course, there is some z velocity as well. You can look at, wait, what happened? You can look at vorticity. I mean, since the newer version saves vorticity as well. Had it not saved these, we can also calculate vorticities in ParaView itself. Okay, sorry. So how do you calculate these vorticities yourself? So you go to these filters. Um, where is that? Okay, unstructured elements. Okay, now there is a filter which calculates gradients. It's not this one that I'm looking for. I'm looking for something else which is not here. Okay, it's okay. But you can calculate gradients and vorticities right here itself. For example, if you do this, I can calculate vorticity square. So you can select vorticity, raise it to the power 2, and save the results in a new variable called entropy. Okay, if you apply this, you'll get entropy, and this you can plot. Okay, you can plot these as a surface. So you can calculate other variables as well. So if I could find that that filter which would calculate gradients, you can calculate vorticities as well. Anyways, so you've seen how to read these XDMF files and this thing. Again, there are several these several functions here in the paraview itself. So let's use this threshold thing. So you can set threshold on quantities like let's say if I put a threshold on UX, let's say I want to see only the positive quantities, the positive view velocities. I do not want to see backflow, or let's say I want to see only the regions where the flow is backwards. There is backflow there. So I'd set the upper threshold as 0. So it will show me all the values that are from negative 0.9 to 0. Okay, if I apply this, so you see it shows me the region where the velocities are less than 0. So this blue region is essentially the cylinder where the velocity is 0, and behind the cylinder in the wake flow there is some reverse flow happening there. So you can put thresholds like this. Now, if you remember the famous images like papers showing you hairpin-like structures in turbulent flows. So to get those hairpin-like structures, you have to get vorticity and apply a threshold on those vorticity. Now, if those vertical structures are shaped like a hairpin, then you'll see those hairpin-like structures. Maybe I can show you that I have these TBL simulations as well. Okay, let's see if I can show you. Okay, so these are the TBL simulations. For this, I have quite a lot of files, so you can see the turbulent flow developing. So I'll play this. Can you see this?
Yes,
It's
it's visible.
it's in a very small region close to the wall, but it's done this way so as to so that the solution is not affected by um, the boundary condition here. Anyways, we'll stop this thing. Okay.
Let us take a 10-minute breaks now.
Oh, okay. Sure, sure. Okay. Oh, so Venkana left, right? Okay. Okay, we'll take a 10-minute break. We'll be back here at 3:25.
Yeah.
Okay.
We can start now.
Okay. Let me see if I can try if I can do what I was trying to do. So what I'm doing here is I'm defining a velocity vector u using these three components ux, uy, and uz. Okay, so this I hat, j hat, and k hat are the unit vectors. I'll apply this, and on this thing, if I see if I have that filter. So the filter is called gradients of unstructured data set. Why it is not there? Anyways, let's. Okay, so mm, so we have seen this thing, the TBL simulations as well. Let me see if I can show how I can show you how to plot the ISO contours for vorticity. Calculate entropy again by squaring the vorticity. Apply. And now we have entropy. So okay, on this thing, we'll use a threshold. Okay, so we see that the range of values that entropy has is from almost 0 to 1600. Not 1600, 160. So let's use a threshold on this one. So this cube that you see here is to specify a threshold. We'll specify a lower threshold of one. Let's say. Okay, let's apply this. So Okay. 1, 2 ones. I still cannot see them. Okay. So there are these contours, but they are very small. Let me do something. So I have entropy surface. I'll take a small clip of this box, not this one. So okay, now we'll plot these isocontours. Okay, so you see this is an intense vertical structure here. What happened to it? No, so these are regions which has entropy values higher than 100. So I can change this value to 50 and you'll see more number of such structures here. I can click apply and you'll see there are greater number of these structures being found here. Can go even lower, let's say 15 or 10. These are still blob-like structures. You do not see hairpins here. But they might be inside somewhere. So no. Okay, so these are isosurfaces on the of the entropy that we had calculated. So it is creating a surface from all those points which has an entropy value of 1. So okay, so this isosurface that it has created, all the surfaces here has an entropy value of 1. So only obviously there's a lot happening here and we cannot see anything. So maybe a higher value will help. Anyways, so that's how you see those isosurface plots, which shows you hairpin or other kinds of vortices in the flow. Okay, so that's how you can use ParaView for these. You can there are several other functionalities which you can use here, but I mostly use this for only plotting these ISO contours. Okay. And you know these movies that you had seen. If you want a movie like this one, so let's put a clip here as well. Bottom this one is. Okay, let's be done with this ParaView and MATLAB. I hope you understand how to process these data output files that you get from Compact.
Yeah.
That was, I think that was a little too much. Anyways, I'll show you a few cases on how to, once you have compiled, how to run these. Okay. Let's do away with these. So I told you to install the Ubuntu subsystem. So I'll run this. Okay, from here I'll navigate to the folder that where my installation files are. Okay. So usually in Linux you have a root folder. So this I'm in root folder now. So you see all these things here: boot, dev, etc., etc, home. You know. So if you go to mount, it will. So here is in the mount folder, you'll see all your drives, C, D, and E, all those things. So you can go to mount. This is where your C drive and D drive is there. These are your Ubuntu installations. So I'll just navigate to my installation folder now. From C, use users. Okay. So I'm in my installation folder. You see, these are all the compilation files that you had seen earlier that we got by compiling. The XCompact 3D is the what the executable, and you see this cylinder folder is for the cylinder case. There is the TBL. Folder is for the TBL case. So first we'll run that channel flow case. We'll navigate to the examples folder. In the examples, we want to go to channel flow. There are several input files here. We'll use this input.i3d. Okay, so what we'll do is these double dots are used to go to the previous folder. So I went to the use this jumped twice to come back to the original folder I was in. Okay, so this is the this is again the same folder here. I'll make a directory for channel flow case. Dir. So mkdir makes a new folder. And I'll copy the input file in examples channel input.i3d. So this is the path for the file that you want to copy and the destination where you want to copy. So I want to copy to the channel folder that I have just created. I'll move to the channel folder. This input i3d file is here. Okay, now let's look at this input i3d file. So as you remember, we had talked about these parameters. So you see I type flow type is 3, which is channel flow. You have these parameters here. So what I'll do is I'll change a few of these parameters the way I want them. So I want to use 4 rows and 4 columns for my domain decomposition. Let's keep this mesh size. This is a bit coarse, but I just want to demonstrate. Domain is 8 times 2 and 4. For my simulations, I've used 12. I mean the domain length in X. In Y it is twice, it's 2, and in Z it is 4. The Reynolds number used is 4200. This is a new addition to the code from the older versions if CPG is T. Okay, so you can specify the friction Reynolds number as well. But we'll stick with this one, specifying the large scale Reynolds number, which is based on channel half height and the mean flow the oncoming velocity u. In stepping, number of iterations will reduce the number of iterations here because I just want to demonstrate. Want to perform DNS, so we'll keep this 0. There are no scalars. We do not want to use IABM. We'll leave the initial boundary conditions as is. Okay, so the boundary condition in Y is non-homogeneous. In X and Z they are homogeneous. Okay, down here we do not want to change anything. So, okay, you can also specify probes. So if you want to put a probe somewhere in the flow, you tell the number of probes and the point for those probes. So this is again is a new addition in the newer version of the code. In the older version, this is not there. So you can change this if you want, according to your needs. That's it. With these changes, I'll save this file. Let's see. These changes have come into effect. So okay. Okay, so now that you have your input files, your executable, all you have to do is run. So I'll use my MPI run command. So it will execute it in a parallel program. I'm going to use 16 processors. The executable is in the previous folder, so I've used double dots xcompact 3D. And you have to specify the input file as well, which is in the current folder. The single dot is used for the current folder. So you specify input i3. Then you. So it will start running. Okay. So I think it will be over very soon. So let's see. Okay. So, in this case, the solution would have hardly converged. You see these divergences. So at each solution step, whenever it prints out these, you'll see it plots the divergence in U star. So U star is the the velocity before correcting, and after correction, the velocities that you get, it calculates the divergence in U. So the divergences are of the order of -13 and -14, which is what you expect for a sixth order code, because your dx and dy's, if I show you, well, your dx, dy, and dz are of the order of -2. So for a sixth order code, you'll get somewhere around, your divergences should be less than 10 should be less than 10 raised to power -12. So these are there. Now, if you go for a coarser mesh, your divergences might, so your velocity solution might diverge. So if it happens, you use a finer mesh. Okay, so I think this will reflect here. Downloads and compact 3D. So you see we have this channel folder now. We have the data. Output is empty. Okay, so this output is empty because what Incompact does is, show you, it calculates average statistics after a number of iterations. So you see, we have specified I output here. Uh, Frequency for visualization. No, this is not it. So there is a parameter which specifies when you have to, when it starts collecting these velocities for calculating average statistics. Okay. So since we had not run this code for that long, the average statistics output is not here. So that's why this folder is empty. We had 4 probes. So the output file for those probes are here. Those the YP values are here. Okay. And the data that is generated. Okay, did not save any data because we did not reach uh, this frequency. So if we run it at least for 5,000, we should have done this, change this. So if it had run for 5,000 iterations, it would have saved one file. I think uh, this was all for in compact. Do you have any questions for this? I mean, okay, I can show you how, I mean, whether the code is, I can show you my channel flow results from the older code. So this is the computational setup, 12 times in X, twice in Y and Z. And the grid resolutions that I had used, it gives me some delta X and delta Y. Eta is the Kolmogorov scale that we had talked about yesterday. We got some mean velocities, which we plotted on this semi-logarithmic scale and RMS, and they're compared with earlier publications. So the code gives you once the solution converges, gives you good results. Likewise for TBL as well. I haven't checked for the TBL, but I expect it would be good for that as well. So okay, so with this, we're done with Incompact. We can talk about the John Hopkins database as well. Okay, so the thing about Incompact is people have published, there are, very new research is being done using these codes and some very fundamental flow situations. So for a TBL, you can see there is this dissipation scaling. So there's work being done on dissipation scaling on a turbulent boundary layer. For a channel flow, the problem that I'm working on is also a leading one. So it looks at the energy cascade in physical space in a wall bounded flow situation where there is a lot of inhomogeneity. Or you can also look for other scenarios, like if you want to simulate a wind turbine. I think there is an example for that as well. We haven't run it, but you can try it yourself and see what it brings. Okay. So yeah, there is an input file for that as well. Okay. So let's move on to John Hopkins database. If you have any questions for before that, you can ask. Yes, no.